Hello and welcome to this program. My name is Mira Kuchibuzo Marcel, and I am an astronomy educator from Nigeria. I'm also very active in research. However, the kind of research that I carry out are those kinds that require the input of ordinary people. We call them citizen science or citizen research. So I founded the Pan African Citizen Science E-Lab to use a platform to spread these kinds of astronomy research in Africa. So we have so many citizen science programs that are being carried out in our research group, and they are here. So the first one you have here is the Pan African Asteroid Search. Okay, we hunt for asteroids, mostly the ones in the main belt and the near Earth asteroids. We also share programs on universe citizen science campaigns. Here, participants can help in classification of galaxies and also help in the hunting of new planets collected from space telescopes and ground-based telescopes. We also have programs on image processing and web telescopes. We carry out research with these web telescopes through Institute of Astrophysics and Lascaux Observatory. Of course, we have telescope time. We also teach our participants how to produce beautiful images from these telescopes. We also have programs for space competitions. We sponsor that so that Africans will be active in some of these international astronomy activities. Then we have Python for astronomy. So if you're interested in any of these activities, you can contact me from with my details here. So the bedrock of our program today is on astrophotography image processing. So astrophotography image processing is simply, learning how to combine images of space telescopes or ground-based telescope to produce beautiful images. So before we go into that, we would like to acquaint ourselves with some of the terminologies and technologies used, and that will bring us to our table of contents. So we're going to learn first of all what filters are. We're going to learn types of filters, CCD, and telescopes, requirements, and basic steps. So what are filters? Filters are devices that modify the light entering the telescope eyepiece either by blocking certain wavelengths or by enhancing specific colors. They are useful for astrophotography because they can reduce light pollution, increase contrast, and reveal faint details and create artistic effects. Filters, when you are taking an image of a particular object in the sky, you have light from different sources, and all this light end up saturating your images, and that's not fine. So we use filters to block some of those unwanted light sources from entering our telescope or from entering our filters, sorry, our telescope. So types of filters, we have narrowband filters and broadband filters. These are the major filters that we use in astronomy. We also have solar filters and so on and so forth, but these are the ones that will concern us for the purpose of our lesson. So broadband, or you call them wideband filters, are designed to transmit a wide range of wavelengths, such as visible spectrum or the infrared spectrum. They are used to capture natural colors and details of celestial objects, such as planets, stars, galaxies, and nebulae. They can also improve the sharpness and clarity of images by reducing atmospheric turbulence and chromatic aberrations. And we have examples of such kind of filters. We have the red, the green, and the blue. They are normally called RGB filters. So look at the kind of filters. So if a white light is incident on this filter, it removes the other colors and allows the red to pass through. The same thing with this one, the blue filter and the green filters. Also remember that these are the primary colors. So if you combine them in the right proportion, they would give you white. And these three colors are responsible for most of the colors we see in our daily lives. The combination of them would give us different colors. So that's about that. Then we have the narrowband filters. Narrowband filters are designed to transmit a narrow range of wavelength, usually corresponding to specific emission lines of gas, cloud in space. They are used to isolate and enhance the contrast and color of certain features such as hydrogen alpha, oxygen 3, sulfur 2, and nitrogen 2 regions. They can also reduce the effects of light pollution and moonlight by blocking unwanted wavelength. And these are examples of such filters. This is hydrogen alpha, hydrogen beta, oxygen 3, and sulfur 2. And these filters are mostly used in observing regions of nebulae or star forming regions because the three elements mentioned here are the building blocks of these regions, like these stars. And if you observe very well, the hydrogen alpha is red. It's red in color. Sulfur is also red, but a different shade of red. And the oxygen 3 is in cyan, a little bit of greenish, blue and green combination. So you call it cyan. And this is better, hydrogen better. So for instance, if you combine the colors from these three elements that I mentioned, which is the sulfur, the hydrogen, and the oxygen, like these are their colors. If you combine them, the result would be this. But this is not good or ideal for visual illustration because there's no much difference between the sulfur and the hydrogen. So to be able to distinguish between these two most especially, we need to reassign them to a different color so that we can distinguish them. So for that, and the oxygen being the one that has the highest frequency or the lowest wavelength, we assign it to the blue color. Okay, then hydrogen we assign it to the green color, and the sulfur we assign it to the same red color. And so when you combine these three colors, you would have this beautiful image. And this is very good for visual illustration. At least you can see vision where there is much sulfur or much hydrogen or even oxygen. And this brings me to an important question. Sometimes some of our participants ask me some important questions. They'll they ask questions like, assuming that I were to be at this point in the universe, will I be able to see this object in this form? And my answer is no, you won't be able to see it in this form. You would see it in this form. We are just using this for visual illustration, at least to map out some visions where a specific gas is much dominant. So this does not really give you the information about the gases, and the elements present. So we have this technology called the CCD. A CCD, meaning charge coupled device, is a type of sensor that converts light into electrical signal. It is often used in cameras or telescopes for astrophotography because it has high sensitivity, low noise, and good dynamic range. So a CCD camera can either be color or monochrome. So, for instance, the commercial cameras that you have or your smartphone camera are made up of this color CCD. So they give you the color of the object in real time. You don't need to take the pictures in gray or in RGB and combine them later. As you are focusing on that object, you are seeing the color in real time and you take the picture. So it doesn't really take much time. Then we have the monochrome. This is the one we use mostly in astronomy. Okay, this is the one you use the broadband and the narrowband filters with. So this is an example of that filter here. So this is the CCD. This is the whole CCD component, and you see these filters of different colors mounted on it. So observe what is going to happen as white light from a source enters it. the filters breaks it into different colors. And then you have these heaps of pixels. By the way, this CCD converts the pixels to the computer language, which is in zeros and ones, and an end result is what you will see now. And here's the result. So that is the work of a CCD in a camera or a telescope. So for the purpose of this lesson, we shall be using images from the Hubble telescope, the Webb telescope, and the Las Cumbres Observatory. You can use images from different places, but what I'm going to teach you here will serve as the basics into image processing. So here are the cameras of the Hubble telescope. We have the wide field and planetary camera too. There are 45 filters in this camera, but this is the old. It has been changed with this new one, which is the wide field camera 3, which has 62 filters. We have advanced camera for surveys. We have the near infrared camera, a multi-object spectrometer. So in total, you have about 145 filters, but the unique filter is up to 100 because some of these filters repeat in some of these instruments. Then we have the James Webb Space Telescope and some of the filters. And in total, we have about 29 filters, but a head count of the filters would give you 26. The reason is because some of these filters repeat in some of these cameras or instruments. So some examples of filters you would see in the Hubble Legacy Archive, we shall see that in the future, are F502N and F606W. The F prefix indicates that they are filters, yes, while the N and W suffixes denote narrowband or wideband respectively. So other types of wideband filters you would see are these. Sometimes you would see this M, LP, and X. These are also wideband filters, okay? But they are a kind of experimental kind of filters. So M denotes medium, LP denotes low pass, and X denotes experimental or custom. We're going to see that as we proceed. Filters are typically labeled according to their wavelength in nanometers. In the RGB color model, red light has the longest wavelength, of course, and followed by green and then blue. If you want to colorize your space image in RGB, you can assign filters to appropriate colors as follows. So for instance, if you have a particular object in the sky taken with these different kinds of filters, which one would you assign blue, green, and red? So the one that has the longest wavelength indicated in these numbers here, we go to the green, we go to the red, followed by the green, and lastly, the blue. For instance, if you look at these filters, maybe they were used to take image of a particular object, and you are looking for the one to assign the red color. So you would notice that 658 is the longest wavelength here, followed by 660, 656, and followed by 502. So if you want to assign these colors, this one would come as red, this one here will come as green, and this will come as blue. And by the way, this is for the narrow band filter. And for the wide band filter, and this is just a rough example, okay? So for the wide band filters, you would assign blue to the one with the shortest wavelength, followed by green, which is this one, and followed by red. So red always assume the the, the longest wavelength. So previously I was describing CCD and filters, and I said that when white light hits the CCD and the filters in the CCD, the filters separate like the kind of accept some colors and reject some colors. So so if you follow what I was actually saying, it means that if you this one was taken from the red filter, this image was taken from the red filter, and this is taken from the green filters, and this is from the blue filters. But in reality, that is not what happens. In fact, these filters actually remove all the colors from the image and only show shades of gray like this. That is what happens in reality. So when you are using these RGB filters, you have these gray images. You don't have them in this form. So we input these colors with our computers when we are trying to process them. So when you color this one with red in your computer, you color this one with green and this one with blue, and you combine them, it gives you the real color of the object. So it is not this way when you are collecting it from the observatory. When you're collecting from the observatory, they will look like this, gray. So when you come into your office to process them, you are the one to add those colors. So this is exactly what is happening. So the requirements for you to be able to process your images are you need Fit Liberator. It's a program that helps to convert your fit files to TIFF files because we are working with, like in astronomy, we're usually working with fit files. So it helps us to, this program called Fit Liberator converts our images from fit to TIFF. And we can also use it to stretch our images. Then we have Photoshop. I'm going to be using this Photoshop in the meantime. Then we have PixInsight, GIMP, and Sausage. We have numerous other programs, but I will be limiting myself with Photoshop and GIMP and Sausage in the future. So the basic steps are once you've downloaded your images, that's the first thing you should do is to stretch it. To stretch it, then you add the colors, and after adding the colors, you will clean it up. You clean up your images, and in this cleanup, it involves removing some pixels that are not supposed to be there. Okay, some pixels that are not part of the image, and also you enhance some part of the image to bring out the details. But one important thing I want you to know is that images from these telescopes have been stacked and calibrated. Also, images taken with space telescopes often do not have noise in them, so you don't need to worry about these. So, and that is the end. So for now, I would like us to download this Fit Liberator. I would like us to download it. So you come to your Google, you type in Fit Liberator. If you type it in, it will bring you to this Google page. Then you click on the first part. When you click on the first part, it will land you here. It will land you here. So this is the Fit Liberator. It's one of the most popular program we use in image processing. In image processing, it's a very powerful program. So you can read down to see these guidelines. So, and I'm going to attach some link. Some of this link I'm going to attach it to the description so that you would learn how Robert Hurt was able to demonstrate how to effectively use it. I'm not going to go into details on how to use the Fit Liberator. So I'm going to give you a link to the tutorial of Robert Hurt. But what I would do is to just go into the basic parts. To the basic parts, you can read down to see some other important information. So to download it, you have to click on Fit Liberator. If you click on it, click on Fit Liberator. Then I use Microsoft, so you can If you're using Microsoft, you can download this. And if you have other formats, computer formats, you can download these other ones. So you can go ahead to click on the one that works with your operating system. I've already done this. So once you have done that, you come over here, and once you've downloaded that, you come over here and you install it. So in our next program, we shall be delving into the Hubble space, sorry, into the Hubble Legacy Archive. Thanks for listening.